I've got a couple of examples here of trig expressions that can be simplified using trig identities. The basic concept here is going to be that you're going to get kind of a complicated expression and you're going to try to break it down by replacing, and you're going to try to write a simpler expression basically by replacing statements with things that are equivalents, okay? The primary things that you're looking at are things like secant is the same thing as 1 over cosine. Cosecant is the same thing as 1 over sine. Cotangent is the same thing as 1 over tangent. Okay, those are all reciprocals of each other. The big thing is you're using sine of an angle divided by cosine of an angle is the tangent of that angle. The sine of an angle squared plus the cosine squared is equal to 1, and tangent squared plus 1 is equal to secant squared. 1 plus cotangent squared is equal to cosecant squared. Okay, but basically we're trying to replace parts of statements with equivalent statements. Now, a follow-up on this. I usually will pick these statements in a way so it will simplify down to a single trig expression. In a standard math book, that's not necessarily going to happen. You might get something that's simpler than what you started with, but it's not always going to work out to be exactly just one trig expression. Okay, again, I really just did that to kind of help you guys along with the process so you can kind of say, hey, I think I'm done now, I'm down to a single trig expression. So again, as far as I know, the vast majority of the ones I've assigned will simplify down to just one trig function. Might be squared or something like that, but just one trig statement. But again, that doesn't have to happen. It just will in most of these because I chose them that way. All right, so the first one here. One of the strategies that can be important, and by the way, there are a lot of ways to do these problems. So, you know, I may show you something and you may do it totally differently and get exactly the same answer. And that's something that people consider to be good sometimes and other people consider to be bad. Anyway, a lot of times I'll take the reciprocal functions out. I'll try to get myself back to just sines and cosines. And in fact, some people try to convert every statement to just sines and cosines. They'll replace tangents as well and use this thing here and try to get an entire statement that's all sines and cosines. I usually try to get rid of the reciprocals, but a lot of times I'll leave tangents, okay? It just depends. Anyway, in this case, I know that cosecant is the same thing as 1 over sine. Okay, so I'm going to replace that. And if you have parentheses, writing the statement into a different form so you can get some cancellations and simplifications, that's always a key. So if there are parentheses, multiplying parentheses out might change it in a way that gives you something that simplifies. If there aren't parentheses, maybe you can factor out a GCF or something like that and change it in a way that something will simplify down. So just in general, trying to replace things with equivalents, but also trying to write a statement in a different equivalent form. So I know I can use the distributive property here. Sine, of course, is sine of theta over 1. I'm going to multiply it by this. That's going to give me sine of theta over sine of theta. Okay, and then minus sine of theta times sine of theta, that's sine squared of theta. Okay, we're not done yet though. This is equal to 1. Okay, so I can take that statement out, I can replace that with a 1. Okay, 1 minus sine squared of theta. Now, this statement looks pretty good. You might be thinking, hey, we're done. Okay, but I noticed there's a sine squared of theta, and there is a trig identity that has to do with the sine squared of theta. Remember, you can rewrite these statements into other forms, okay? I can try to get a statement from this that would give me a 1 minus sine squared of theta, and I could see, is that equal to something that's simpler, okay? So, if I have sine squared of theta plus cosine squared of theta is equal to 1, and I want to have a statement that's 1 minus sine squared of theta, if I subtract sine squared of theta over here, I also need to subtract sine squared of theta over here, okay? But I can get an equivalent statement. So that's going to go away. I'm going to get that cosine squared of theta is the same thing as 1 minus sine squared of theta, okay? And by the way, the other version of this works too. If you subtract cosine squared from both sides, you'll find out that sine squared is equal to 1 minus cosine squared, okay? That's pretty important. Anyway, so 1 minus sine squared of theta is the same thing as cosine squared of theta. So that whole statement there is the same thing as cosine squared of theta. And again, as I said on these basic problems here, most will simplify down to a single trig statement. We've got a cosine squared, we're done, okay? We're not going to get any simpler than that. All right, let's move on to example number 2. I think I'm going to take this one out here to give myself a little bit more board space. Example number 2, we've got a sine squared plus a cotangent squared. Okay, cotangent squared is 1 over tangent, which can be very useful. But also remember that tangent is sine over cosine, and cotangent then would be the reciprocal of that. It would be cosine over sine. So some people will prefer to try to replace almost anything that's got a tangent or a cotangent with some version of sine over cosine. Okay, I don't do it every single time, but in this example I think it's going to be helpful. So I'm going to leave that sine squared of theta just like it is, except I think I'm going to write it as sine of theta squared. Okay, and cotangent squared of theta, that's the same thing as cotangent squared. Cotangent is the reciprocal of this. That's going to be a cosine of theta divided by a sine of theta. And then remember that the whole statement is being squared here. Okay? So actually that setup's probably not super useful. I'm going to multiply this back out. I'm going to write that as a sine squared of theta again. I think that setup will be a little bit more useful. I'm going to write this as a cosine squared of theta and a sine squared of theta. So you can go back and forth between different forms. And remember, these are being multiplied together. That is over 1. So take a look at what I'm going to get here. When I multiply this out, I'm going to get a sine squared of theta times a cosine squared of theta. In the bottom, 1 times sine squared of theta is sine squared of theta. Remember, when you're simplifying a fraction, you should always divide a greatest common factor out of the top and the bottom. Notice, you can divide a sine squared out of the top, and you can divide a sine squared out of the bottom, and that's going to leave you with just a cosine squared over 1. So this statement here is going to simplify down to cosine of theta squared, or you can write that as cosine squared of theta. Nice problem. All right, moving on to number 3. All right, for number 3, we got a cosecant squared minus a cotangent squared. We got a 1 minus cosine squared. All right, there are a whole lot of different things going on here. And this one, I have a feeling, a lot of these, there's a very long, complicated way to do it. There's a very straightforward way to do it. Sometimes you try something and it works terribly, and then you decide to go a different direction, okay? One of the things that I'm noticing here, anytime you see a sine squared or a secant squared or a cotangent squared or something like that, I always ask myself if I can link to one of the trig identities here and get something to work out. And one of the things that I noticed here, there's a link between cosecants being squared and cotangents being squared. And I notice I have a cotangent squared here as well. And so I was kind of wondering, well, maybe if I try to write everything with cotangents instead of cosecants in that numerator, maybe something nice will happen and this will kind of simplify it. So I'm going to do it this way. I'm going to keep the negative cotangent squared of theta, and I'm not sure what's going on with this denominator yet, so I'm going to leave that as 1 minus cosine squared of theta. Cosecant squared is literally the same thing as 1 plus cotangent squared. So in place of this, I'm going to do a 1 plus cotangent squared of theta. And check it out. I've got a cotangent squared minus a cotangent squared. That just adds up to 0, okay? It's going to leave me with a 1 on top. And the bottom here, 1 minus cosine squared of theta. Well, if you think back, if I subtract cosine squared from both sides of this statement here, I'm going to be left with sine squared of theta on the left-hand side, and I would have a 1 minus cosine squared of theta on the right-hand side. So 1 minus cosine squared of theta is the same thing as sine squared of theta, okay? So that's 1 over sine squared of theta. And you might say, well, we're down to a single trig expression. We can leave it here. I will say, right now it's a reciprocal, and the reciprocal kind of makes me uncomfortable here. I would probably flip this. Different ways you can do this. Technically what's happening is we have a 1 over sine being squared, right? Because 1 squared is 1, sine squared gives me sine squared. 1 over sine is the same thing as the cosecant, okay? And it was being squared. So we could say cosecant squared, or we could say cosecant squared of theta, okay? Now, if a bunch of you looked at this, if you notice, 1 over sine squared, you could have said, oh, the reciprocal of sine is cosecant, it's being squared, that's cosecant squared. A lot of people will just jump straight to that step, but I wanted to show you why it actually works. Okay, so cosecant squared for that one. I've got a couple more examples. I'm going to do those in another video.